we are going to have one in which we are going to go over specifically to all the different kind of storage systems that we have available on the CECI clusters that you can use from your, you must use for running your jobs. And we are going to take a look at how each of them is set up and how each of them works in order to make an efficient use of each of them. So in the Indico website, I guess you're used to navigate through it, but you can find the if you go to the timetable of today's session, you can find here on the icon, you click there, then you can open the PDF and download it on your machine if you want to. Follow it on your screen. So first, before going into all the details about the different kind of storage system of the clusters, we start with a big warning. It's just, it is mentioned on the documentation, but sometimes it's, we already had on the past, unfortunately, system failure that ended causing data loss on the CECI clusters. You must always remember that we don't have any kind of backup. We do have in place all the storage system of the cluster. They are heavily used. So there's in place different, especially RAID setups that allow to avoid the situation of having data loss because 1 or 2 or 3 hard drives dying, or even a storage server dying. So there are systems in place because actually we are changing this of the storage systems every year in all clusters. But we can never rule out a really bad situation that unfortunately we had in the past. That we have several disks dying, a big batch of disks dying one after the other before we are able to take care of replacing the failing parts. So you must remember that, so you can use the CECI, you use a CECI cluster for running your jobs, or you will produce output, and you must remember that to get that data out of the clusters and copy it somewhere else to store it for the long term. So the useful data that you will need then for your publication. So there's a link to the CECI documentation. The different CECI universities, some of them they provide solutions for long-term storage. You can check that link and then see the contact at each of your universities. And yeah, well, now in order to follow properly for the topics that we are going to deal with on this presentation and the small exercises that we will see at the end, you must be kind of already familiar with all of these previous presentations that we had in October and November last year. In any case, we are the kind of, especially with preparing and submitting jobs with Loom, as we will see a couple of examples on how to submit jobs using the different storage targets. But the jobs that we will see, they are very basic, very simple, just to illustrate how we should script them. So in it will work as a refresher of how do you submit jobs. Just as we are going to discuss about storage I/O and how to efficiently use them, we will see a little bit about the speeds, the access speeds to the different storage systems that we have on the clusters, to getting some numbers to see where we are standing on. Nowadays, on a single machine, so on a laptop or a workstation, the most performant single units of storage, long-term storage that we have on a single machine are NVMe SSDs. And if we run a benchmark job in which we write, we are in the most ideal situation for doing output to the storage. We write a single file, a sequential file. We do a sequential write of a single file of 2 gigabytes. Yeah, we will see that with this kind of devices, we are on the order of the gigabytes per second. So here, testing on this laptop I'm using for the presentation, and getting on the NVMe of the laptop 2.5 gigabytes per second right into the SSD. But yeah, here we are. We have the CPU accessing an NVMe, so the CPU is accessing the storage unit directly by the PCA lanes of the machine. So I'm showing this just to then we will see the values that we will get for different storage places on the cluster to see where we are standing. Because if you follow it, but yes, you must be aware an HPC cluster is this was shown in the very first presentation by Frederic. An HPC cluster is a cluster, a group of machines that we call compute nodes, which are the goals, which are the ones that are going to do the computation. So on these machines, we are using the CPU and the RAM that they have. Yeah, they might have or not some local storage unit, but then all this group of machines, they have access to so they will have access to storage systems that are accessed via the network. So we are not at all on the case of, as I showed before on the laptop, that the CPU access directly to the storage unit via the PCI Express lanes of the CPU. So we are, most of the time, on an HPC cluster, we are accessing the storage, your home directory, and if you already took a look at what we call on the CECI local scratch and global scratch, they are most of them, only local scratch is an exception, but most of the storage is being accessed via the network. And the network is order of magnitude below than what we will get via a PCI Express access on a single machine. But we will see that we can do, even via the network, different kind of things, depending on the kind of jobs, in order to increase the output efficiency. So yeah, it's important that you get familiar with this, with how an HPC cluster is built, and then and keep in mind that when you're logging in and you are by default on your home, this login node, which is a machine with a CPU, RAM, motherboard, might have some local disk. It does have for the OS, but your home directory is already being active. It's on another set of machines, and it's being accessed via the network. Well, in the previous presentation this morning by Damian, among the different topics that he covered, he actually mentioned that for network storage solutions, we can kind of divide it in two big groups without going into further details into each group. But yeah, in this kind of two big groups division, we can have one group in which we are having our storage server access. We can see it as a single machine and a single network uplink. And then all the clients, so in the HPC cluster case, the login node and all the compute nodes are accessing this storage server via a single network uplink. I can have more than one link for redundancy, but just in practice, I can see it as a single network uplink. So you can imagine that on the clusters, we are having about 100 compute nodes. So and each of them, they have multiple cores, between 24 to 64 cores. So you can imagine that when, on the case of Lemaitre3, we have about 2,000 cores in total. On NIC5, it's 4,000 cores. So you can imagine that, and most of the time, the clusters are almost at full capacity of the core's usage. So imagine how this can be, how this network access can be badly required when you have 2,000 jobs that at some point they are not doing output right into disk at the same time. But so this can be easily saturated without even using the 2,000 cores, but even less. And so then there's another paradigm for providing and storage accessible via the network, and this is kind of the other big group without going into the details of the different kind of setup that we can have. In what we call a parallel or a distributed file system, we have I still have a file system exported via the network that I will see as a single. It's a single namespace exported via the network. I would see it still as a single file system, but it's actually divided among different storage, different physical machines. The single file system is split it and scattered among different physical storage servers. But they are aggregated, and I will see it from my clients, login nodes and compute nodes, just as a single file system. But the fact that I'm using different machines with different network uplinks, it allows me to increase the output to that storage solution for my clients. And so after that introduction, we are going to I'm providing here another schematics similar to the one that Frederick presented. So it's a schematic of an HPC cluster. So we have the login node, which I can have just a single one or two or three, or I can have several login nodes. So the login node is the area where when you do SSH, Lemaitre3, NIC5, Dragon 2, is the machine in which you end up when you do SSH to the cluster. You are on what we call login node. And you land by default on your home directory. You can print, if you do echo $home, you can print the full path. The important thing to remember is that this is a network provided storage. It will be visible from the login node and from all the compute nodes. But it's a different storage solution accessible via the network by all of them, by the login node and all the compute nodes. But and then when you submit a job, on the login node. So you will write your Slurm script. You will ask for resources for your job, specify your input and where your binaries are, and run your job, and you submit it to the queue. And at some point, it will be scheduled and it will start running on one of the compute nodes or on several compute nodes if it's a several multi-node parallel job. But still for the home directory, the compute nodes are accessing it via the network. But so for the first kind of storage space that we have on the CECI cluster, that we name it local scratch, it's actually storage units that are physically inside on each of the compute nodes. So they are like local disks on your computer. The local scratch are disks, but they can be HDDs or SSDs, but that are inside of each compute node. Then, yeah, of course, this is accessible only by the compute node hosting this, having this disk inside. It's just identical as a laptop or a tower workstation. It's the disks inside the machine. The advantage of this kind of storage device is that, being inside the machine, I can usually have a good performance for accessing it. I'm accessing it directly via SATA lanes, if it's SATA, or via, well, we don't have any SSCs NVMe inside the node for the moment. But yeah, we're accessing it directly, not via the network like a home directly. But yeah, but this kind of this space, it can be used during your job runtime. So when your job is scheduled on compute node 2, then you will have an environment variable we will see later, but which is called $local scratch, that will point to a directory that you can write, but during your job runtime. So you can set up commands on your Slurm script to do CP, to $local scratch, to copy there, to retrieve from there, to CD there. But those commands will be only meaningful inside the Slurm job. You must take into account that when the job ends, this directory, temporary directory that you have during your job runtime is removed. So on your script, you will have to retrieve before the end of the script. You will have to add CP commands to recover the data, the useful data, like for instance to your home directory or somewhere else. And this area will be meant to use for serial jobs or single core jobs or parallel jobs, but which can run on a single node. They can be NPI jobs if you're running all your tasks on the same node, or if you are running shared memory parallel jobs, like with OpenMP or Python multiprocessing, or that kind of parallelism that you're on the same node, then you can profit of just writing to local scratch. But then on all the CECI cluster, we have there's another area which we call it for the CECI cluster global scratch. Here the dollar also points that we are defining this path by an environment variable. So if you log into any of the cluster, you can do an echo of $global scratch. Here, as the name implies, it's a globally available storage area. So it will be available from the login nodes and all the compute nodes. So in this case, you can just echo it as you go in. For local scratch, it's not defined on the login nodes because they don't have local scratch. You might have a dummy variable defined, but it's not really what would be the local scratch on a single job. But global scratch, yeah, it's a network file system implemented via different CTOPs on the different clusters, depending on for which kind of jobs the cluster is targeted. But yeah, in all cases, it's a globally available file system, and then by definition, if it's globally on a set of different compute nodes, it's accessed via network interconnect. And basically, we will have the case of a single server providing the global scratch a little bit like the home directory, or we will have a parallel file system in which the global scratch is built by different storage servers. And yeah, and this area, this target storage will be actually the only option for like big MPA jobs. MPA jobs using multiple nodes, then your only possibility is to do all your I/O there. You will have the home accessible, as I said, but you must never use the home for doing I/O of big jobs because yeah, you can easily get the home access saturated, and then all user of the clusters won't be able to do even an LS of their home. And so I already mentioned, as I was presenting them, the fact that I was introducing them with the dollar before is because, yeah, these areas, they are defined with these environment variables. So for home and global scratch, if you log in, you can print the path. And yeah, local scratch, it's only meaningful inside Slurm scripts. So what now going into the details on how they are actually set up on two of the CECI clusters, so for Lemaitre3 and NIC5. They both have a dedicated parallel file system providing the global scratch. It's as mentioned from Damian's presentation, it's a file system that is distributed. I see it as a single file system, but it's actually distributed among different storage servers. Each of them has its network uplink. Yeah, that way I can, with that kind of aggregation, I can increase the I/O to this storage target. And yeah, for the case of yeah, also that allows me to the fact that I can stack different storage servers and they provide me a single file system means that I can easily scale up the amount, the full net amount of storage size provided. On a single machine or a single storage server, I'm limited to the amount of hard disks or SSDs that I can attach to this single machine. But here I can just add servers in the network. It allows me to reach really amounts that I cannot think of in a single machine. So for you, yeah, to have an idea, the net size of the global scratch file system on Lemaitre3, so on both is about 500 terabytes, about half a petabyte. So that's another advantage of this kind of solution of parallel file system. It's not only increasing aggregating the server for having more I/O, but allowing me to really build a storage solution that I cannot reach on a single machine. So for the persons who will have big problems having to deal with big data sets, this allows you a possibility that you will hardly have on a single workstation. The case of on these two clusters, the local scratch, they are quite small because this, as mentioned on the documentation, these clusters are mainly targeted, especially for big MPI jobs, for big parallel multi-node jobs. For that reason, it's invested when these machines were acquired. It's decided to invest part on the machine acquisition or having a big dedicated parallel file system. Because you can imagine this kind of solution is more expensive than having just a single machine with this providing a network file system just from that single machine. And some things to remember, in principle in Lemaitre3 there are no quotas enforced on this on the global scratch area. On NIC5 there is in principle a 5 terabyte hard quota implemented. But it's a good, so this is shared among all the users of the classes. So you are free to use it for to profit of them and to use it for the amount that you need. On NIC5, even if it exists this 5 terabyte hard quota by default, for a particular run you need for a couple of days, weeks, month, a bit more, you can contact the local sysadmin and explain what you need to run, and it can be increased on a case-by-case basis. So the idea is that if you have a problem for which you will need to either read or write a lot of, or both, a lot of data, you can profit of this exists. It's a reason for which the CECI clusters exist. But remember to clean up once after you finish all your calculation, you did all your post-processing. It's really important that you remember to recover the important final data that you will need to keep. You copy it somewhere else, as I said. You notice there is not. Notice that both area they have the scratch part there. So the idea is that they are temporary usage. They provide good performance, but they are not the most resilient in the case of having hardware failure. So remember to it's a good practice that you must develop once you did it for all your calculations, copy over, recover the important data somewhere else, and please clean up the global scratch area, especially the local scratch. As I mentioned before, that area, it's a folder that you have available only during the job runtime, so it will be erased when the job is done. In the case of the Lemaitre3 and NIC5, the local scratch areas, they are not that big. It's just they are SSDs of 200 gigabytes or 370. So take that into account if you're running, if you're going to use that. Take that take that into account, and this will be shared among all the jobs running on the node. So we have 24 cores on the NIC3 and 64 on NIC5 complete nodes. So we go now to okay. Well, so this is just some extra information about the BGFS file system, which is the one providing the parallel file system on Lemaitre3 and NIC5. So it's the Wikipedia entry for BGFS. You have there some there's this area showing some benchmarks done with a BGFS setup of having a lot of here. They are stacking up to 16 different storage servers. As you can see, well, here is mentioned that on one of these single storage, one of these single machines building up my storage cluster on the local file system, without BGFS, and having the account of the order of 1 GB per second write and read. But so building up them together and accessing them as a BGFS file system. And of course, and then having some special job that is able to profit of this doing. You have a special code that is able to do parallel I/O. You can scale up the output bandwidth almost with the. You can increase your output if you keep increasing the amount of storage servers that you have on the cluster. But it's very important that this is not magic. You need your code to be able to profit of this kind of hardware that you have again. So you do parallel I/O. Actually, you write to the different storage servers on parallel. But still, this kind of solution allows you to go over the limit that you have on a single machine. It is one of the reasons because of why HPC clusters exist. So if now going into the details on how Hercules is set up, Hercules is meant for not it's focused mainly on single core jobs, so serial jobs, or on parallel jobs, but which can run on a single node. And then the architecture of the cluster is for the global scratch is different to NIC5 and Lemaitre3. We still have a global scratch, which in Hercules you will have an alias. Will be called global scratch or $work deal, but they point both to the same storage space. So it's a dedicated storage area for doing I/O on your job if you need to a globally accessible scratch space. But it's set up similarly to like the phones. So it's still a single storage solution. It's exported by an NFS share to all the clients. So it won't be as performant as the one on the Lemaitre3 or on NIC5, but it's the one you must use on Hercules if you need an area. A globally accessible, just because not only we will mention that on the script, but you can use it for doing I/O of your job, but you can also use it. So the idea is always to prioritize the local scratch usage if you're on a single node. But as I mentioned, the local scratch is deleted when the job is finished. So for instance, here you can profit of copying over from local scratch to global scratch at the end of the job instead of recovering it to the home. The home quota on all cluster, it's always small. It's kind of small. The idea is that you keep there your input file, your scripts. So it's always smaller than what you will have on local scratch and global scratch. So one usage you can make of Hercules, if your job they fit fine on the local scratch for the I/O, is to copy over the data that you will need for other jobs or the output of your job that you will recover later. You can copy over to over scratch. And in the case of Hercules, it's more focused on running serial jobs or parallel but single node jobs. Here you have the local disks that are bigger than what we have in Lemaitre3 and NIC5. You have different generations of machine on Hercules. So the nodes named from the nodes number 65 to 96. So which are the oldest. They are Intel Sandy Bridge machines. They have 1 terabyte array 0. The local scratch is speed of array 0 HDDs, and the full net size that you have on the oldest is 1 terabyte, and then you have another generation of AMD machines providing 4 terabytes in this local scratch folder, and then you have 2 special nodes that they have 2 terabytes of RAMs, the high-end nodes, and they have 8 terabytes in this local scratch. And then the last CECI cluster, the one at Mons, available now, Dragon 2 at Mons. It has a kind of different setup. Kind of special setup for the global scratch. So you still have the local scratch, so the local disk, the local storage space on each compute node, which is in this case built of array 0 of 3 hard disks, and you have 3 terabytes on each compute node available this storage target in each compute node. But then there's also provided a global scratch area, but it's still being set up with the BGFS file system, but differently to NIC5 and Lemaitre3, where you have dedicated storage servers, so fully independent machines from the compute nodes, just providing your storage cluster. In this case, the parallel file system, it's built up by small small partitions from the local disks. So you have different bricks if you want. Each brick is a small partition on each compute node, and all these bricks they provide you the global scratch area. So you will see it again as a single file system, but the data is actually scattered among all the compute nodes. So here, I think that you are sharing the network interconnect of all the compute nodes to build this single parallel file system. And yeah, so also Dragon 2 is focused, is also focused for single, for serial jobs or parallel jobs running on the same node. So always prioritize the use of local scratch first, and yeah, you will actually have a more perf in writing to local scratch, either to rather than global. Yeah, I think yeah. Also the advice is the same. In the case of Dragon 2, there are no car quotas. There are no quotas enforced on the global scratch area. But please remember to be not, especially here, that yeah, it's not that big. So 50 terabytes it might be big for a single user, but the CECI cluster they have about between 200 and 300 active users for years. So.
The advantage of this architecture compared to having
no, actually, this is a kind of solution to provide something, but it will be always more advantageous to have a dedicated for this year, to have a dedicated cluster of machines that are just doing that just are providing a parallel file system service. This is you have the compute nodes and then you can build it. But so there's a lot of so you can imagine that the fact managing this thing, you have a lot of different services that you have to run on each machine. So that consumes CPU, that consumes RAM. Because this kind of parallel file system, you have calculation to do to split the data or move it and decide. You have a disk that die and you have to decide to move data. So it consumes resources to run a parallel file system. So having dedicated hardware to provide it will be always more advantageous than doing this. And yeah, so up to here, we were talking about each cluster and each storage possibilities that we have part of the cluster. So they are locally to the cluster. The thing is called global is just because I can access it from all the login nodes and compute nodes, but it's still a solution local part of each cluster. And now well, if you've been already taking a look at the documentation about the storage usage, you will see the mention to the CECI common storage. I don't know if someone else has questions so far, or yeah, what would, or you can. Yeah, we have time to more questions then at the end also. So for the CECI clusters, it's provided a part of what we saw so far to the moment. Another storage solution, which is called the CECI common storage. And this is, it's the name implies this is a storage that is available from all the CECI clusters. It's a set of different machines, dedicated storage machines, to provide this storage area for all the CECI clusters. So from all the CECI cluster, you can access this single entity this thing that you will see as a single entity, but it's actually a distributed set of machines, even in different cities. But yeah, we will see a bit more of detail on next slide. But the thing that you need to remember, from all the cluster you will see, but you must remember that this is fully external to the cluster. Each cluster has next to it what is called a gateway to the common storage. It's a it's a small storage server doing some caching. So when you from Lemaitre3 you write to the common storage, you are actually directly physically writing on this gateway machine, this cache machine. It's a machine with it's a small storage server. Small is 50 terabytes in this case, and you will write there, and then this machine has it's set up as part of this common storage is provided by a parallel file system, and this machine is part of all the services which are part of this file system. So you will write physically to this machine, and then the service part of this parallel file system solution will take care of copying to flushing this cache from time to time to copying over to the common storage. So when you write there from Lemaitre3, you will not maybe immediately, if you will connect also at the same time to NIC5, you will to this common area that you write, you will not immediately see it on NIC5, but after some seconds or minutes at most, the data will be flushed and copied to the common storage solution, and then you will see it available from the other cluster. So the idea of this solution, it was a long-term request by the researchers as they are distributing the workloads among all the clusters. It's to provide some kind of solution to move data from one cluster to the other, or to store common data that I need to use as input for my jobs on all the different clusters. So it's a solution that provides that. It provides a single, for the user, it's just a single location that you can access from all the clusters. But keep in mind how is architecture, this thing, on the sense that I mentioned that you should never do I/O from your job to your home. So you should even less do direct I/O to this solution that it's a kind of complex solution with this gateway being feed the data and then looking to the common storage. It will be for sure actually less performant than writing to the global scratch or the local scratch. But it's another area that you could use at the end of your job. For instance, you're using the local scratch at the end of your job, copy data there for storing it, for using it later. But it's by no means it's part of the storage system of the CECI cluster. It doesn't have backups. It's by no means to be seen like long-term storage. So the idea is to provide an area that you will see transparently from all the clusters, but don't think about it as long-term storage. So in the as I mentioned, this solution actually it's built so the data is physically distributed on two big storage machines. There are two big ones in back here at the UCL. There are two other big ones at UDH. And yeah, the data, all the data that I have on the storage servers of the UCL is mirrored with the storage server of UDH. That means that if the full UCL availability, so of course I need, in order to build these solutions, yeah, I need a network allowing me to communicate among the different storage servers of the solution. So at each site, I have this gateway machine that will dump the data to the storage servers that are at the UCL and UDH. But yeah, you can imagine that I need this can require the network among this machine quite a lot. So we have actually a dedicated fiber provided by Belnet, so the network provider of all the universities in Belgium. We asked them for providing a dedicated fiber that we use for the communication between all well, especially for the gateway machines at the ULB, Mons, and Manu, to communicate with the big storage at the ULB and UDH. And then, yeah, the fact of having a mirror at the UCL and UDH means that if this network connection that we have, we lose the UCL for some reason. If we are still, the rest of the sites are still able to reach Liège, I will still be able to access the data. But yeah, you can imagine the complexity of the solution. So the idea, yeah, is that it's to provide this common area, but not to provide something super efficient for doing I/O from my job. And so in this, so how do I access this storage area from the cluster? So we have all the different shares from this storage. They are mounted on each cluster on these mount points: CECI Home, CECI Proche, CECI TRSF, and CECI Soft. But then inside CECI Home, yeah, there will be actually a full path similar to, actually equivalent to the one of your $home. That provides you a folder where you can write there. And that path is pointed, for easiness, is pointed with the $CECI Home variable. So if you log into a cluster and you do echo $CECI Home, you will see the full path, which is yeah, a personal area for you to write on this share. And it has a quota of 100 gigabytes. So whatever you write to there, to CECI Home, as I said, a couple of seconds or a minute later, you will have it available if you do ls $CECI Home or that path from any other cluster. Then there's an area which is meant, if there's a group of users that needs well, to share data among, so a group of users of the cluster that need to share data among them. It can be whatever, input files, output files, binaries for the codes that you run in so codes. So instead of each of you having the same copy of that data on your CECI Home or on your global scratch, a PI of a lab can request a special area, but it can request the creation of a project, which a storage project, which well, explaining a bit which are their needs, and then a quota is set, is set on that area. A folder inside there is created, and we provide the full path to the users involved, and then all these users are will be able to write to this, to read and write to this, to a subfolder inside the CECI project. And then we have the CECI TLSF here, which is okay. So here there was a change on how this works. So CECI TLSF is also nowadays is a personal area for each user. So if you log in on a cluster and you do echo or ls, but echo $CECI TLSF will give you the full path. So each user has a personal subfolder inside CECI TLSF. Here you have actually a quota, a more generous quota. You have by default 1 terabyte soft and 10 terabyte hard. And the idea of this area is to, so I mentioned before on the global scratch, especially of Lemaitre3 and NIC5, you have up to 500 terabytes to use. So you might have sometimes to move a lot of data that you have, for instance, in the global scratch, like 5 terabytes or 6. And you will need it to move it from the global scratch of a cluster to the global scratch of another. And then you can profit of this area for that. So you can dump there 5 terabytes, and then after when you see the data accessible on the other cluster, you recover it on the other cluster. So from the CECI TLSF to the global scratch of the other cluster. So that's really the spirit for which this area is created, meant for moving especially big amount of data from one cluster to another. If it's just a small amount that fits on your CECI home, then you do it via your CECI home. But so what means soft and hard? So the up to 1 terabyte you can write on this personal folder of CECI TLSF without any restriction. But if you go over 1 terabyte, let's say that you write 3 terabytes, you can, but then you will have a countdown that starts after you go over the 1 terabyte. You have a countdown that starts that allows you to keep writing during 1 week. So during 1 week or up to reaching the 10 terabyte mark. So you can write at once the 3 terabytes, but then you will have 1 week of a grace period, and after that you won't be able to write anymore after the 7 days. So the idea of that setup is that you will then you need to move 3 terabytes from Lemaitre3 global scratch to NIC5 global scratch. Then you can do it. You dump your 3 terabytes. You recover it from NIC5, but then you should clean up the data that you copied to CECI TLSF. That we are hardly doing it, but we can do it, or we can request you to do it. If we see that you are over quota, at some point we will contact you asking you to please remove the data there. Or we can, from time to time, delete all data from non-active users. But don't be surprised if at some point you receive an email asking you, please, you're over quota here, please, you should do cleanup. And well, here you have the link to the CECI documentation about more details on how to use the common file system. And then I talked that you have home, CECI home, global scratch. Some of them have quota, some not. So if on a given cluster you don't know how much data you are using or how much data you have on the common area, so there's just a single command, CECI -quota, enter on any cluster, and it will provide you your usage, the limit. And yeah, I didn't mention, but yeah, on some file system we have enforced also a limit on the amount of files, because yeah, that's information that must be kept also. Even if you have a lot of small files, that they don't take up a lot much disk space. Each file that you have is still information that the file system must have on where that file is located. So and actually each file system has a limit on the amount of files it can be aware of where each file is. On some, especially, so that's for the common storage, it can be an issue. So there's also in some file system a limit on the amount of files. So here it will show you how much files do you have on CECI home, which limit there is. So remember that you can get over quota not only on the amount of space used, but sometimes on the amount of files that you have. I already mentioned from during the presentation that we have the cluster predefined environment variables for controlling the access to these different areas. And then for a Slurm job, which you're going to script, you will have to script how to move data from your home to the local scratch, or the local scratch to the global scratch. And sometimes you might need to create a folder. You are going to run a job, and you are going to write inside global scratch, and then you need to avoid, and then you are going to submit a second job with a different input. So the same code but different input, and you want to write to a folder on global scratch. So you have these two useful variables, especially Slurm job ID. So you've been submitting jobs already. You saw that when you submit a job, that the job gets an ID, which allows you to monitor the job. That job ID is a unique value on each cluster. So you can use that variable to create, for instance, a unique folder. If you do mkdir global scratch / Slurm job ID, then you know that you will have a unique folder there on global scratch with the number of your job ID, and then you can copy your input there, and you do your output, and then you submit a second, third, 5 job, and you know that each one will be writing on its own folder. But here, this is just an example, to kind of compare with what I showed at the very beginning, what kind of values, just kind of grosso modo thing, and because I ran this for testing, please don't run this. So it's just kind of the DD command that I showed, but on my laptop that was getting like 2 gigabytes per second, doing a sequential write of a 2 gigabyte file. So if we do the same thing, we write a sequential file. We do a sequential write of a 2 gigabyte file on the different storage targets that we have on the cluster. So this is the kind of thing, but you must not run this. And I run this with the cluster on production with a lot of other jobs being run. So I'm not here benchmarking the maximum birth that I can get. It's just to have an idea of what happens here for the cluster in production. And you can see, so this is an example of running this for Lemaitre3. you can see that for both the scratch areas, I'm on the gigabyte per second. And then, yeah, writing on home, on CECI home, I'm like an order of magnitude below. Notice, yeah, what I was saying, yeah, writing to CECI home. Yeah, even if I'm actually writing to this cache next to the cluster, I'm still with less perf that I get even on the phone directly. But so this is just to remember, yeah, the main thing here is that you must learn to use local and global scratch for your jobs. You will get, if you're writing 10 gigabytes, here it takes 10 seconds, and here it will take 100. So yeah, on all read and write operations, you will get less time by using the scratch areas. And here is the example on Hercules 2. Here, as I mentioned, we don't have a dedicated parallel file system. So the value that we are getting, we are not, we are on kind of 500 megabytes per second. We are low below what we were on the Lemaitre3, but still we are on a better situation than this home, especially the CECI home. But as I mentioned, yeah, for Hercules, you must, but for a cluster, you must focus on local scratch if your shop I/O fits on the local scratch provided on the compute nodes. Always focus on using it, because then you are not stressing unnecessarily the global scratch usage. Your job is writing to the local disk of the compute node, and you are not stressing unnecessarily the network to access the global scratch. We have on the CECI website here the last link of the quick links. It's also referred via the documentation if you follow the Sloom quick start guide. But the last link of the quick links, I don't know if you've been there already. It has a wizard to help you to build your Sloom shop script. And you can select that you want to use local scratch, global scratch, and it will provide you the commands that, yeah, this will work. They might be just some slight tuning. And yeah, we don't have a lot of time remaining, but we can see, so that was the end of the presentation. We can take a fast look to one of the examples. As I say, they are very, really toy problem, very basic, just to. And then you can check them more carefully on your own, but they will stay there on that folder. So there's just, so on that folder mentioned on the slide, on the presentation slide, you have this. There's some small README telling how to test these examples. So you can copy. You can copy this folder to your home. So then you can. So as you see here, you have a Python code, 2 Python codes examples. This is called my code 1, and this is called my code 2. That we don't think on. Okay. from my code one, it will just it will initialize a NumPy array with value up to a limit that that limit is provided by a number on a file called input.in. So in this example, input.in is just a file with the number 1000. So it will read that number from the file, and it will create an NumPy array of that size, and then each element of the array will be equal to the index. So I will have an array with values 0, 1, 2, 3, 4 up to 1000. And then it will write a file. So this will generate an output file, long.out, which will be just a file, each line having 1, 2, 3, 4. So it will have 1000 lines, and each line will have the number 1, 2, 3, 4 up to 1000. So it's just then, in order to kind of emulate a situation in which I have one job, I write a given output here, long that out, and then I need to run another job to post-process that output. So it might not be the case of your runs, but it's the case of some people. So then I have my code.2 that it will read. So it will initialize an NumPy array by loading this long.out. So I will read and recreate actually the same array. So an array of 1000 elements, and each element of the array is 1, 2, 3 up to 1000. And then I use a NumPy method to adapt all the elements of the array. So what I'm doing is I'm doing 1 plus 2 plus 3 up to 1000. So I'm adding up all the elements of my array. And then it will write the result of the reduction on a file named result.out. So this is and then, so notice that on the README, it's mentioned to create this folder and then to copy, well, here's a typo, you copy my code 1 and my code 2 into that folder, CECI-home/bin. So that's one of the usage that you can have for CECI-home, for instance, to have the binaries of a code that you need to run from different clusters. And so I have the first Slurm script to submit, in which I'm going to request my resources. So just a single core, 50 minutes. Well, I'm requesting a lot for not even a second that will run, but and then I load the modules that I need in order to have NumPy available on my environment. And then I will copy this file that I name in my folder input underscore 1000 and to local scratch, and there I will name it input.in because my code is actually waiting for input.in. But in my local folder, I might have a different input file named somehow that they are prepared with different kind of inputs. I might need to run my same job for different values of a given parameter. So I can have my file's name in order to know what the contents are, but then I copied it to local. I will copy it to local scratch as the generic file name expected by the program. I cd to the local scratch, and then I run my code being there. And then, as I said, local scratch is a folder that exists on the compute node during the job runtime only. So I know that my code will produce long.out, and then I must remember on my script to recover that somewhere else, the long.out. And I do it using this, the this variable that I didn't detail on the presentation, slurm submit dir will be equal to the folder where I run the dispatch command. So here I'm doing dispatch job local scratch 1 to schedule it, and the full path of the folder where I'm running dispatch. So this full path will be equal to the variable slurm submit dir. So for that reason, I profit of that to recover. I'm telling here, copy the long.out that will be greeting on the local scratch of the node to slurm submit dir. So I will recover it to my home here in this case. I don't know if it's running. So at some point here, I should get my when the job is done, I should get my long.out file. There is a message I get on the module load command. Okay. So the job ended, and I got here on where I did the dispatch. The log.out that I said is a file. Just like name. Okay, from 0 to 1,000, and then I have my second job to submit. To process the output of the first. So I'm copying. I will submit this. And I copy the long.out to local scratch. I run my code 2 that will read this file, and then it will add up all the numbers that it found on that file, and it will produce result.out. So if you, just for curiosity, if you want to actually see that if your job is going to run for long time and you want to see what it's writing, you can, as during your job run, I don't know if it's already finished. You can, you can SSH to the compute node where your job is running, and here it makes sense. Actually no. It could be added an echo to scratch. Okay, so by default, well, my job is finished, so I got kicked out of the compute node. But on the case of Lemaitre3, the local scratch on the compute node it will start always by that, like /local scratch, then your username, and then the job ID. So note that this was, you see the job ID. So that will be the local scratch folder. Local scratch, your username, and the job ID. And here it was the long.out that was written there. So now this should have brought the result.out with the value, the result of adding up the long.out. So you can SSH to the node and take a look at the local scratch folder only during the job runtime. Then when your job is finished, you are not even able to SSH. But the different clusters have different approaches for defining global scratch. So you could add also an echo. So before doing operations there, you can have an echo of $local scratch. So then on the slurm.out file, you will get the path. You will get the path printed. of the local scratch folder. So then you can easily know. Yeah. So when you check where your job is running, on which node, then you can, yeah, you know where to SSH and immediately where to look for, if you want to monitor the files as they are being written. Because yeah, for sure you will have jobs that don't run on seconds, but on hours or days. So that was the example, and the one for global scratch is using exactly the same this toy problem, but here but the difference here is that, yeah, global scratch is already an area existing on the, so we said it's a global storage for the accessible from the login nodes and the compute nodes. So I can, if you do echo global scratch, you will see that you have a personal folder created there on the global scratch area, which is persistent. It's not that local scratch, it is removed at the end. So if you are going to do I/O there on different jobs, you have to remember to create for each of your job, you must create a unique folder where you're going to copy your input, where you are going to CD, and where you are going to run your job. And then, yeah, your job will yeah, here I will fix it then in the, here I forgot about it. So in this case, so there are some advice here. You can do whatever you wish to create the unique folder for each of your different jobs. But they are, let's say, two common practices: either to name it by something that is related with the input that you use for that job. It can be yeah, your code or whatever, and some values related with the input. So in this case, in this example, I'm using that kind of approach. So I create a folder called my job 1000 because I'm running it with the input of value 1000. But another approach, yeah, if you are going to run a lot and you don't want to think about what you will to hard code for each script, what a different folder name. You can just use the slarb job ID variable, so then you know that you will get a folder name inside global scratch. There will be a slash, a job ID number, and then all your input will be there. But yeah, remember, you could use also, this is a bash, this is a script in bash language. So you can use, you could use, if you have already a set of 100 files, all prepared with different inputs and all named differently. They must be named different. I lost the Wi-Fi connection, but yeah, you could do a bash loop to loop over your input file for this instruction, the mkdir, with a variable there in the run-dir definitions and the same variable pointing to your input. So yeah. that's another approach to automatize them. And so here, in this case, yeah, this run, it saves the output, and the output then it will be a global scratch. My job, 1,000. Yeah, there it was copied the input.in, and it was created the long out and finish. So then there's the second job will just run the script 2. It will here I know that this already exists, so I just define the run near, I cd there, and I run my code 2. So these are just two small examples of this toy problem of the kind of workflow that you might have on your different, more complex runs, like this kind of pattern of exploring a lot of input parameters on a given code. Well, it's quite frequent, and that was it. And finish it again with this warning, because it's very important that you remember that. Please don't remember to copy over, to back up the data. After you finish all your set of runs, process it, and that data that you need to keep, remember to copy it somewhere else outside of the CECI cluster. This is the very last. So the main advice is, if your job allows it, use local scratch. On all clusters, it will be so if it will be the most performant file system, you won't be stressing the network to access the global scratch. So prioritize the usage of local scratch if the size of I/O that they are going to do allows it. If it doesn't, then you must go with the global scratch. And for multi-node jobs, you don't have another option that using global scratch, but please use global scratch for multi-node jobs and never that was it.